Now let's move on to the next big question in cosmology. What is the ultimate fate of the universe? We've already seen that the objects in our universe change over time. In stars, there's a constant struggle between gravity and internal pressure, which causes the star to evolve as it changes chemically and runs out of one after another source of energy. Galaxies also evolve as the stars and gas within them change and as they collide with one another. But what about the universe as a whole? How does it change? We've already seen one important part of the evolution of the universe. It's expanding. So the key question to ask is, will this expansion continue or will it change over time?
Before the late 1990s, scientists considered just 3 likely answers to this question, and they were based on the overall average density of the universe. The first option was that the universe would only expand so far, and then gravity would make the expansion stop and reverse itself. This would happen if the average density of matter and dark matter in the universe was larger than a certain value, known as the critical density. A universe that expands and then contracts back on itself is known as a recollapsing universe. On the right, we see a diagram showing the relative size of the universe over time, with the recollapsing universe shown in red. You can think of the recollapsing universe as the what goes up must come down model. In the same way that if you throw a ball up in the air, sooner or later it will fall back to the ground. In this model, the universe starts out flying apart, but sooner or later gravity pulls it all back together. The opposite extreme is one in which the density of the universe is less than the critical density. In this case, the expansion keeps going forever. In the figure on the right, this is shown as the coasting universe. It effectively means that the gravity of the universe is too weak to slow down the expansion. A way to visualize this is to imagine standing on a small asteroid and throwing a ball upward. If the asteroid's gravity is very weak, then the ball won't fall back down. Instead, it will keep flying away from the asteroid forever. The last option is called the critical universe. In this case, the universe is exactly at the critical density. The expansion keeps slowing down here, but never quite comes to a stop. Here's another picture to help you see what's going on. On the left, you see the recollapsing universe, which starts at a point and expands for a while before collapsing back to a point. On the right, we've got the coasting universe that expands outward without slowing down significantly at all. Finally, the critical universe is in the middle, expanding at ever slower rates, but never quite turning around and recollapsing.
Try explaining in your own words why density is important in determining the fate of the universe. To do this, you might think about other times where we've discussed the role of density in topics like the formation of stars and galaxies. So what kind of a universe do we live in? To find out whether or not the density of the universe is larger, smaller, or the same as the critical density, there are 2 basic approaches we can try. First, we can simply estimate the average density of the universe, including all of the dark matter, and compare this with the critical density, which depends on how fast the universe is expanding. In other words, the critical density is tied to the Hubble constant we saw a couple of chapters ago. When we do this, we find that the visible matter makes up about 4% of the critical density. When we include in the dark matter, it comes out to 30% of the critical value. This tells us that we are in a coasting universe that will keep expanding forever. However, there's another approach, and that is to see how the rate of expansion has changed in the past. To do this, we need both distances and speeds to galaxies that are billions of light years away to see whether they were expanding apart at the same rate that things are expanding now.
We can measure speeds to distant galaxies easily using redshifts. As we saw earlier, measuring distances is more challenging. We can't use the Hubble law here because we're trying to test how constant the Hubble constant really is. In the 1990s, astronomers began using white dwarf supernovas as an accurate way of measuring distances to very distant galaxies. However, when the supernova distance data came in, it provided a surprise. It didn't match any of the predicted models of the expansion. Instead, it showed that the expansion of the universe has been speeding up rather than coasting or slowing down. This is like throwing a ball up into the air and having it go faster the higher it goes. Since these initial observations, there have been many attempts to find errors in the supernova distance measurements. But even with several independent groups working on the problem, it's clear that this acceleration is real. So now we have a fourth model for the expansion, known as the accelerating universe. Exactly what this will mean for the fate of the universe depends a lot on what causes the acceleration to occur.
In order for the expansion of the universe to accelerate, there has to be a source of energy. There's evidence that this energy would have to represent around 70% of the mass energy in the universe, bringing the total up to the critical density. The name we give to this mysterious energy is dark energy. There are several ideas about what dark energy could be, but no well-tested model for it yet. One set of approaches to this involves something known as the Casimir effect. Particle physics models predict that incredibly short-lived virtual particles should be appearing and disappearing all of the time everywhere in the universe, even in complete vacuum. These particles have a measurable effect in the lab, known as the Casimir effect. The Casimir effect is measured when we bring two parallel plates very close to each other. We find that there is a force pulling the two plates together because the density of the virtual particles outside the plates is larger than the density between them. This effect has been measured now for many years, and it is used to calibrate models of how these virtual particles behave. Unfortunately, the simple calculations of the energies involved in virtual particles come up with values many orders of magnitude larger than that observed for dark energy. Either something is causing only a small part of the Casimir effect energy to play a role in the expansion of the universe, or there's some other effect entirely behind the dark energy. At the moment, this is the cutting edge of modern physics, so it may be some time before we have an answer to these questions.
We know that the expansion of the universe is currently speeding up, and it's reasonable to ask if this acceleration will continue indefinitely. In fact, the answer depends on the ratio of the amount of pressure associated with dark energy to the total energy density of the universe. At the moment, we don't really know what the ratio is, so it's difficult to figure out what will happen to the current acceleration we observe. However, if this acceleration continues, then the expansion of the universe will keep getting faster and faster. Eventually, distant galaxies will simply disappear from our view, followed by parts of our own galaxy as the expansion rate overcomes the gravity holding it together. In principle, this could continue until stars and planets and even individual atoms are torn apart by dark energy in a big rip. Over a century ago, a set of observations led to two great revolutions in physics: relativity and quantum mechanics. Looking around at physics today, if there's going to be another great revolution like this, it's likely that the acceleration of the universe will be a big part of the motivation for it happening. The Nobel Prize Committee recognized this a few years ago when they awarded the prize in physics to the teams that first discovered the acceleration in the 1990s.
We've looked at both dark matter and dark energy in this chapter. Just to help you keep them straight, try sorting this list of statements into the fields for each of these.